Good morning, guys. I hope you're doing well today. We're going to be talking about Lecture 3 today, and so I'm hoping that this will help you to understand some of the materials that are in that. Again, if you have any questions, comments, problems, please let me know. I would appreciate hearing from you if that is the case. A preference, again, is to have you note the timestamp and the lecture, and then email me or come to one of my office hours with any questions that you have. All right, so let's get started in Chapter 3. Review questions. What is the full electron configuration of arsenic? Arsenic. Well, okay, I'll tell you what we should do here. Wait, hold on. I apologize. Let's slide this over here. Right. Let's see if we can see it. Full electron configuration of arsenic. Well, if I look at my periodic table, which I have in front of me here, I see that arsenic is number 33. All right, 33. We're in the 4th row. So that means that I have a configuration that starts with argon. That was what I wanted to do. And it did ask for the full electron configuration. So if we want to do the full electron configuration, I need to do 1s2, 2s2, 2p6, 3s2, 3p6. Now that's the core. That takes us up through 18 argon. So 2, 4, 10 electrons, 12 electrons, 18 electrons. So that takes us to 18. Now we're going to go to row 4. We're going to go 4s2. And then we drop down to 3d. And I know I'm full in the 3D because I'm all the way over in the P section on row 4. So since it's 3D10, remember 2 electrons per orbital, 5 orbitals, so 3D10. And then we have 4P, 1 for gallium, 2 for germanium, 3 for arsenic. So that's how we get there, okay? What is the formula for dinitrogen pentoxide? N, there's 2 of those, oxide, pentas 5. So N2O5. What is the abbreviated electron configuration of silicon? So let's find silicon. That's number 14. So the nearest noble gas, and I'm actually going to put this over here, is neon. So we have a neon core. We then come down to 3s2. And then 3p2. All right. What is the name of Fe2CO33? All right. Well, I know that Fe is iron. I know that CO3 is carbonate. So we're talking about an iron. The charge on that iron, based on inspection, is 3. Because I know that carbonate is -2. So we need to put that in Roman numerals in the parentheses. And then carbonate. Awesome. What is the formula of rubidium phosphate? Well, rubidium is Rb, it's number 37, which is an alkali earth metal. So it's going to be a plus. I know that phosphate is PO4 3 minus. And that means in order to make this neutral, I need Rb 3 PO4. Okay? Yahoo, we did that. What's the name of NH3? Well, NH3 is ammonia, but it's also nitrogen trihydrate. That didn't help. Trihydride. And hydride sounds weird. It should, but that's what we call hydrogen when it's negative. Okay, so that's what we're talking about there. All right, pick an atom. Symbol, atomic weight, common ions. Pick one ion and write its electron configuration. Well, I'm going to need some space for that, so let's clear this. Clear my canvas. So, let's pick an atom. What should we pick? Well, I don't want to pick my favorite one because lead is way far down the table. So let's go ahead and choose oxygen. And I'm going to choose oxygen because it's one we work with a lot. So I know that oxygen is 0. I know that it's number 8. Symbol, atomic weight is 16 per this periodic table. And it's common ions. Well, O is 2 minus. I also know O minus, but it's not very common, so you don't actually need to write that. Pick one ion, let's go with the O2 minus, and write its electron configuration. Well, okay, if we look at the base electron configuration for oxygen, we could either do He 2s2 2p4, or we could, instead of the He, we could have 1s2 2s2 2p4. That's what it looks like when it's an atom. But we know that we want to do the O2 minus ion. So I've added 2 electrons to this. So instead of being this configuration, we're going to have 1s2, 2s2, 2p4 plus 2 is 2p6, which makes sense because if we add 2 electrons to it, then it looks just like neon, and that's the electron configuration for neon. Okay? Does that make sense? I hope so. If it doesn't, let me know. I'm going to go ahead and clear my canvas so that we can try and do some other things. All right. And I'm going to make this bigger again and go back to the slideshow. So hopefully there are no questions from that, but if there are, please let me know. I'm more than happy to answer any questions that you may have. Nuclear structures, isotopes. So if there are a fixed number of protons, neutrons, and electrons in an atom, why are all the numbers for atomic masses not whole numbers? Because we know that a proton is approximately 1 atomic mass unit, a neutron is approximately 1 atomic mass unit, and those electrons are really, really tiny, right? But they're not all whole numbers. Why is that? And it's because we have different isotopes. And we talked about some isotopes last time. Isotopes differ only in the number of neutrons that they have. So if we're talking about a particular element, like oxygen, right? All of its isotopes have to have 8 protons. That's what defines oxygen, so 8 protons. But not all of them have to have, say, 8 neutrons. Okay, they can have a number of different neutrons, and that's all dependent on what exists in the universe. All right, so you'll need to know the definition of this and how it affects the mass. All right, also know that A is the sum of the protons and the neutrons. All right, you'll see what that A is in just a minute. That's what we're going to be talking about right here. A nuclide is an atom characterized by a certain atomic number, Z, and a certain mass number, A. We'll discuss this in more detail in chapter 19.1. We do talk about that in this particular lecture. So, A, Z, X. Z is always the same for the same element, okay, as is X. So again, if we're talking about oxygen, then we're going to have an oxygen written here. Let's see if we can do annotate. So we have an oxygen. That's our Z. We know that that's number 8. So it's always going to have an 8 down here for the Z. And this number up here is A. So we have to know the number of neutrons to add to that number of protons to be able to figure this out. I know that one of those things is going to be 8, because if I add 8 and 8 neutrons, that gives me 16 for the mass number. okay? And I know that's one of them because oxygen has a mass of 16, okay? So since we have 8 neutrons for that, we'd put this 16 up here. And that is one of the nucleotides of oxygen, okay? So Z is the number of protons and the number of electrons and the number of electrons in a neutral atom. So A will change, nothing else will. And that A is going to depend on which nucleotide we're talking about. Now I'm going to get rid of this. Hopefully, if I can remember how to do it. So isotopes of carbon. Again, mass number, atomic symbol. Atomic number determines the atomic symbol. Mass number is the sum of the protons and neutrons, both having 1 AMU each. So if we're going to talk about carbon, carbon is number 6. That's why we get this number 6 down here at the bottom. If this is 6, this has to be C. If this is C, this has to be 6. That means we have 6 protons and 6 electrons because none of these are charged. We can have a mass number of 11, 12, 13, or 14. If we have 11 as our mass number, that has 5 neutrons. So 11 minus 6 is 5. If our mass number is 12, then I have 6 neutrons because 12 minus 6 is 6. If it's 13, then my number of neutrons is 13 minus 6, which is equal to 7. If my mass number is 14, we go 14 minus 6, and that gives us 8 for the number of neutrons, okay? Now, these are all neutral ions, right? Typically, when we talk about nucleotides, we're not talking about ions. We're always talking about neutral species, okay? So it's not a charged particle that we're talking about. Hopefully that makes sense, all right? So write the symbols for the following isotopes. Carbon 13. Let's see if we can annotate this again. So we just saw carbon 13, right? So it's a carbon. We know that its number is 6 and 13. Why are you being so difficult? Okay, maybe not. Let's try something a little bit different. Sorry, the annotation was not working very well, so I gave up. So carbon 13. All right. So again, my logic here is carbon is number 6, so that has to be down there. And the mass number is 13. That's the one that they've given you. That's what that 13 means. Okay, we can have radium, which is Ra. I know that its mass number is 228. So that's going to go up here. Now I have to find radium on the periodic table. And dun, 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 where the heck is it? Ah, radium is right there, 88. Okay, it's an alkaline earth metal. So we'll put that 88 down here. And then if we wanted to talk about how many neutrons we'd have, it's 228 minus 88. And no, I can't do that math in my head, so I would have to use my calculator to do it. 228 minus 88. Yay, 140. Because no, I can't do that in my head. Subtraction and division are not my strong suits. Okay, awesome. Let's look at what else have we got. What's the number of protons for each of the above? Oh, sorry, we haven't done chlorine 35 yet. So chlorine is Cl. We know that this is 35 because that's what they gave us. And I know that chlorine's atomic number is 17. So 35 minus 17 equals, and 13 minus 6. And that one's 7. I can do that one in my head. Yay, I can do some things. Awesome. 35 minus 17, 18. And yes, I could attempt to do this in my head and get it wrong, but I don't want to do that to you. So, all right. So we talked about what is the number of protons for each of these? Well, carbon is number 6, so it has 6 protons. Radium is number 88, so it has 88 protons. Chlorine is number 17, so it has 17 protons. So number of neutrons for each of the above. Okay. 13 minus 6 is 7. 228 minus 88 is 140. 35 minus 17 equals 18. And then I say, take a guess. Is that the normal number of neutrons for this material? Why or why not? What the heck do I mean by that? Well, what I'm going to tell you is that if this number and this number are fairly close for small atoms, that makes a lot of sense. So carbon and chlorine definitely make sense, okay? We're not so sure about this radium because this is 88 and this is 140. Is that a good ratio or not? Well, we don't really know at this point. So that may be normal, it may not, okay? At this point, you have no further information from which to talk about that. Now, I've mentioned an atomic mass unit before, and I said that a proton is approximately 1 atomic mass unit, and a neutron is approximately 1 atomic mass unit. We talked about this when we defined those particles. But what the heck does that term actually mean? Well, our atomic mass unit is defined as the mass of 1/12 the mass of 1 carbon-12 atom. So it's one of these guys. So I have 6 protons, 6 neutrons for that carbon. It's a symbol for the isotope. Isotopes are defined as atoms in the same element, which differ by the number of neutrons present in the atom. The mass of 1,6,12C is set to be 12 AMU. How do I know how many neutrons are in the atom? The number of neutrons is the difference between the mass number, 12 for C above, and the number of protons, 6 for C. So the number of neutrons on carbon-12 is 6, right? So that's how we define that mass. 1/12 of the mass here, is 1 AMU. And of course, this is set to be 12 AMU, all right? Okay, that's awesome. Why is that important? Well, we'll get there. Now, just like we can say that a dozen is 12 of anything, we can define a mole as Avogadro's number of particles, one element or compound. Okay, who's this guy Avogadro, and what the heck is his number? Avogadro's number is 6.0221413 times 10 to the 23rd. Generally, we round this to 6.022 times 10 to the 23rd. Now, as I've mentioned before, that number is considered infinitely known, so we don't round based on this. Even though it is rounded, we don't use it as a way to define sig figs. So 1 mole contains 6.0221413 times 10 to the 23rd atoms or molecules. To me, this number is huge and atrocious. I don't want to work with it. I really, really don't. So I can talk about moles, and those are much easier for my mind to conceptualize it. Okay? Molar mass is defined as the mass of 1 mole of that atom or molecule. So if we're talking about the mass of O2, which is a molecule of oxygen, then the mass is defined as the mass of 1 mole of that. I know that that's approximately 32 because each oxygen is 16, so O2 is going to be 32. Okay? Questions, comments, problems on that? Awesome. Molar mass, therefore, the mass of 1 mole of a substance is the same as the atomic mass, provided that you use the atomic masses on the periodic table. Awesome. So we can go from atomic mass units to grams per mole. It's the same number, it's just different units, okay? For most everything that we do in this class, we're going to talk about the mass in terms of grams per mole. Now, do I need to know when it is an AMU? Yeah, kind of, because they might ask you about it on a test. It might come up at some point, but it's really not that important, and most of us hardly ever talk about it, okay? So the mass values that exist on the periodic table take into account the normal distribution of isotopes that exist in that element or compound. So remember I showed you 4 isotopes of carbon, right? Not all of them exist at the same amount, okay? We find that we have way more carbon-12 than the others. Carbon-13 is fairly known. Carbon-14 is also fairly known, and we use that for radioisotopic dating, okay? But their mass in nature is what determines the mass that we see on the periodic table, because we take the weight for that particular isotope and multiply it by how prevalent it is in nature. And then we add all of those things together, and that's that number we see on the periodic table. Does this matter to you? Yeah, probably not. I'm just hoping that you understand why it's not a round number, because that was tricky for me. I didn't really get it. So if I know the mass of a sample of an element, I can know the number of moles that I have, and that will tell me how many particles are present. Okay, what the heck am I talking about? Well, let's see exactly what we're talking about. Again, I'm going to move this over here so that we can deal with this particular whiteboard. All right, clean whiteboard. I say that I have, no, sorry. Didn't mean to do that. Okay. 13.56 grams of lead. And yes, I did mention that lead is my favorite element, so I chose it. Okay, awesome. That's how many grams I have. What is the molar mass of lead? Well, lead, again, is number 82. Its molar mass is listed 207.2 grams per mole. Okay, awesome. So that's its molar mass. How many moles do I have? Well, 13.56 is the number that I start with. And I know that I have this conversion factor. I have 207.2 grams in 1 mole of lead. And I can do that math. That's not overly complicated. 13.56 divide 207.2 gives me 0.06539, yada, 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 yada. Okay, that's a lot of numbers. Where am I going to cut it off when I write it down? Well, I need to round this. So 0.06540. Why do I say 40? And of course, it's not going to fit there. Isn't that annoying? So it is actually 0.06540, or 6.540 times 10 to the minus 1. Why do I say 4 sig figs? Because 13.56 has 4 sig figs. So that's how many significant figures I should have in my answer. Okay, now I know how many moles I have. Well, that's completely awesome. Why is that important? 0.06540 moles. 1 mole contains 6.022 times 10 to the 23rd atoms. And so then I can do that. So I can take this big, huge number. I can multiply that by 6.022 second E23. And that gives me 3.938 times 10 to the 22. And again, that's 4 sig figs based on this, not based on this. Although they do agree, so at this point we're fine. And that is atoms. Okay? Why do I care about that? Because that's the next thing they asked me. How many lead atoms is that? So if I have a mass in grams, I can get to moles. If I can get to moles, I can get to particles. If I'm in moles, I can get to particles, or I can get to grams, as long as I know what I'm talking about. Well, that's awesome. I have conversion factors, and so now I can do math. I love math. But let's talk about what we can do, what other things we can do. So the molecular mass, aka the molecular weight, we use them interchangeably, even though they are really not. is the mass in AMU of one molecule. It's also the mass in grams of 1 mole. It's the sum of the atomic masses for the components in the molecule. So if we want to talk about H2O, we need to take 2 times the number that's listed on the periodic table for H, 1.01 grams per mole, plus 16.00 grams per mole for oxygen. Total for that is 18.02 grams per mole. It's also 18.02 AMU for one particle. Sodium chloride. Well, sodium is 22.99 grams per mole. Chlorine is 35.45 grams per mole, and that gives me 58.44 grams per mole. Now, it just so happens that the periodic table that I use, this big one that I reference when I'm doing these things, it's actually this big table that I have, has only 2 sig figs, 2 decimal places for every number that's there. That's why all of my numbers are rounding the way that they are. Okay, but that is not the way that it typically exists in most places. And the tables that you're going to use on your tests are not like that. So make sure that you're paying attention to that. I know for me, during lecture, it makes my life a lot easier if I don't have to worry about it as much, but that is not the situation that you're going to have most of the time. So NH2,2CO. So remember that we have to distribute this 2 to the N and the H. So it's actually N2H4CO. So 4 times hydrogen, 1.01 grams per mole, plus 2 times the nitrogen, 14.0 grams per mole, plus 12 carbon, 12.01 grams per mole, plus the oxygen, 16.0 grams per mole. And that gives me 60.06 grams per mole, or AMU. Okay? So that's how we find it for a molecule. Now, so we can do atoms, we can do molecules. Go awesome. Calculations using moles, mass, and number of atoms. Well, I showed you this for lead in just a second ago. We can do this ad nauseum all over the place. Would I recommend that you do this ad nauseum all over the place? Yes. Because what we're going to do after this first test is all about conversions. So we want to make sure that this is something that we've dealt with. Okay. So if I have the mass of an element, I can use the molar mass to get to the number of moles of that element. And from there, I can use Avogadro's number to get to the number of atoms of that element. If I have the number of atoms, I can divide by Avogadro's number, and that gives me the number of moles of that element. And I can take that and use the molar mass to get back to the number of grams. Okay, so I can go anywhere from there. Now, if I have a mass, if I want to go to atoms, I need to go through moles. When in doubt, convert to moles. Why do I say that? Because it's almost always what you're going to need to do first. So when in doubt, convert to moles. And we do a couple of calculations here. It says, if I know the mass of a substance that I have, I can calculate the number of moles that I have. Consider oxygen, O2. It has a molar mass of 31.9988 grams per mole. How many moles of O2 do you have if the sample is 267.84 grams? So this is the mass that I start with. This is the molecular weight. So I have 267.84 grams of oxygen times 1 mole of oxygen being 31.9988 grams per mole of grams of oxygen, which gives me 8.3703 moles of O2. Why that number of sig figs? Well, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5. Okay? That's how I got to 5 sig figs. How many and that's what this little statement right here says, 5 sig figs, because the mass of O2 was 5 sig figs. Okay, so that's this mass right here, not the molecular weight, but the mass. How many particles of O2 are there in this sample? For this, we're going to use the answer that we just came up with, this one right here, before you round it. So whatever your calculator says before you round it, that's the one we're going to use. All right, and that's what this is right here. So otherwise you run into rounding errors, and Alex will tell you that your answer is wrong. So 8.370313887 moles of O2 times 6.022 times 10 to the 23rd molecules of O2 per mole of O2. And 5 equals 5.0406 times 10 to the 24th molecules of O2. Since the mass of oxygen is rounded to 5 sig figs, that is the number of sig figs that you should have on your answer. Okay, so those are two examples of this kind of calculation that we're going to do. Remember, when in doubt, go to moles. Go from grams to moles, from moles to particles. When in doubt, go to moles. And if you need to go somewhere from there, you can. Okay? Any questions about that? And I'm going to slideshow again. All right. Let's talk about another fun topic. Percent composition. Percent by mass of each element in a compound. So the percent composition of an element is that thing times the molar mass of the element divided by the molar mass of the compound times 100. Yippee skippy. What the heck am I talking about? Okay, let's see. So let's take and make this tiny. Well, tinier. And if you can see my notes down here, it says, what is the percent composition of carbon in glucose, which is C6H12O6? Well, carbon is 6 of them times the 12.01 grams per mole gives me 72.06 grams per mole. The hydrogen, being 12 of them, is 12 times 1.01 grams per mole gives me 12.12 grams per mole. That's a typo. Good Lord. Oxygen, there are 6 of them times 16.0 grams per mole equals 96 grams per mole. Total mass, if I add all 3 of these together, is 180.18 grams per mole. So the percent carbon is the mass of carbon divided by the total mass times 100 equals 72.06 grams. This one right here, divided by this per mole, divided by this 180.18 grams per mole times 100 is equal to 40% carbon. Okay, 4 sig figs, because I have 4 sig figs. So 4 sig figs. Okay. For the for the hydrogen, we have 12.12 grams per mole divided by 180.18 grams per mole times 100, 6.727 grams of hydrogen. Percent oxygen equals 96 grams per mole divided by 108.18 grams per mole times 100 equals 53.28%. Now, if I do a math check on that, (40 plus 6.727 plus 53.28 helps if you do 40 plus 6.727 plus 53.28. And that gives me just over 100. Okay. And that's what it should be. All right. It's never going to be exact, but it should be damn near 100% because if it's not 100%, we haven't accounted for everything. And if it's over 100%, we have too much of something. So 100% should be what we're looking for. Okay. All right. So that's our percent composition of carbon and glucose. And I also did the hydrogen and the oxygen. Okay. Awesome. What is the composition of each element of ZN3PO4 2? All right. Well, Zn is 3, 1, 2, 3 of them, times 65.38 grams per mole equals 196.14 grams per mole. The 2 phosphorus, because we distribute this, so it's P times 2. 2 times 30.97 gives me 61.94 grams per mole. The oxygen, there are 4 here. We distribute the 2, that gives me 8. 8 times 16 grams per mole gives me 128 grams per mole. Total of those being 386.08 grams per mole. The percent of zinc is 196.14 grams per mole divided by 386.08 grams per mole times 100 equals 50.78. For the percent P, we get 16.04, and for the oxygen, we get 33.15. Okay, and again, let's do a test. 50.78 plus 16.04 plus 33.15. 99.97. And again, not exact, but close. We can use the same process in reverse to determine the empirical formula of a compound. So if the mass percent of sulfur is 40.05 and for oxygen is 59.95, what is the empirical formula for the compound? Well, I have to make an assumption to do this. If this is a percentage and I assume 100 grams, then I have 40.05 grams of sulfur and 59.95 grams of oxygen. So sulfur is 40.05 grams. We convert that to moles to find the ratio. So 40.05 grams of sulfur divided by 32.07 grams of sulfur per mole gives me 1.259 moles of sulfur. Oxygen is 59.95 grams. Convert to moles to find the ratio. 59.95 grams of oxygen divided by 16.00 grams of oxygen per mole gives me 3.747 moles of O. So we put each of those as a subscript. Sulfur, subscript 1.259, oxygen, subscript 3.747. That needs to be converted to whole numbers because I don't see formulas that look like that. So we divide both numbers by the smaller, 1.259, and we get SO3. Okay, so that is my empirical formula for that. Questions, comments, problems on that one? Then let's do some more practice. What is the percent composition of MgCl2? That's our first one. So the mass of magnesium is 24.31 grams per mole. The mass of Cl2 is 70.91 grams per mole. Total mass is 95.21 grams per mole. We take the 24.31 grams per mole of magnesium, divide that by the 95.21 grams per mole for the total, and multiply that by 100. And that gives me 25.53 grams of magnesium. We take the 70.91 grams per mole divided by the 95.21 grams per mole times 100 is 74.47% of chlorine. All right. Yay. Yippee skippy. All right. Mass of the hydrogen, 2.0. Oh, second. This is the second one. What is the percent composition of H2SO4? Mass of the hydrogen is 2.02 grams per mole. Mass of the sulfur is 32.07 grams per mole. Mass of the oxygen is 64 grams per mole. So 2 hydrogens, 1 sulfur, 4 oxygens. Total mass is 98.08 grams per mole. So mass of the hydrogen divided by the total mass times 100 is 2.06% hydrogen. Mass of the sulfur divided by the total mass times 100 is 32.70% sulfur, and 64 divided by the 98.08 times 100 is 65.25. Now again, just to check, I like to check things. Of course, it's not going to let me resize that. Well, isn't that awesome? So let me move this over here. Okay. 2.06 plus 32.70 plus 65.25. Typo. I hate it when I do that. Doesn't let me do some of the things I can do on my physical calculator when I'm on the computer. So 2.06 plus 32.7 plus 65.25. Again, 100.1. Awesome. We like it when that happens. I'm going to put this over here for now. What is the empirical formula for a molecule that has 40% copper, 6.67% hydrogen, and 53.38% oxygen? No? Okay. 40 grams of carbon divided by 12.0 grams per mole, 3.33 moles of carbon. 6.67 grams of hydrogen divided by 1 gram per mole is 6.67 moles of hydrogen. 53.33 grams of oxygen divided by 16 grams per mole gives me 3.33 moles of oxygen. Carbon 3.33, H 6.67, O 3.33. Divide all numbers by 3.33 to get CH2O. Okay. Now remember, empirical formula is the lowest whole number ratio of those components. So that's what we have there. We have nothing else. What is the empirical formula for a molecule that has 31.42% sulfur, 33.0% 31.35% oxygen, and 37.23% fluorine. 31.42 grams of sulfur divided by the 32.065 grams per mole gives me 0.092 moles of sulfur. I can do a similar calculation for oxygen to get 1.96 moles of O, and one for fluorine to get 1.96 moles of F. So I do my same ratio. I have S 0.982, O sub 1.96, and F sub 1.96. Smallest whole number ratio, if I divide by 0.982, gives me SO2F2. Okay? Hopefully there are no questions about that, but if there are, please let me know. I think we're good there. Determining the empirical formula by experiment. Well, actually, we just kind of talked about this. I say that I have a 0.331 gram sample of iron. It's placed in a crucible and covered with powdered sulfur. The crucible is heated until all the excess sulfur is driven off after the iron reacts with the sulfur. The product weighs 0.522 grams. What is the empirical formula of the iron sulfide complex? Okay, so let me think about this just for a second, because my brain, I have to think. I know that I have 0.331 grams that I start with. And this is the iron sample. Okay, so that's before I do any reactions to it. It's just iron. But then I convert it in some way to make some product. Okay, and I have 0.522 grams when I do that. What's the empirical formula of the iron sulfide complex? Well, the sulfur that is required to do that, since we drove off the excess, is that 0.522 grams of the product minus the 0.331 grams of the iron that we started with. That gives me 0.191 grams of sulfur. Now I can convert both of those to moles. So I take the mass of sulfur divided by the molecular weight of sulfur, and that gives me 0.00596 moles of sulfur. Do the same for the iron, 0.331 grams. Lord, I can't do anything, jeez. It's going to bug me. Sorry, I have to fix it because I realized that I made a mistake. This is what happens when you don't have any to review your stuff before you do it, even though I looked it over like 12 times. Apparently, it doesn't matter how many times I look at it until I attempt to talk through it. Okay, so grams of sulfur divided by the molecular weight of sulfur gives me 0.00592 moles of sulfur. That reduces to FeS. Okay, I have checked that math and that is correct. All right. Questions, comments, problems on that particular process? Again, we're going through the same kind of thing. The only thing that's different is we have to calculate how much of the sulfur is used. All right. Determining molecular formulas. So everything that we've done up until this point is to determine an empirical formula, the lowest whole number ratio that exists between those particular components. But we don't always want a lowest ratio. Do you remember we talked about hydrogen peroxide, H2O2? Its empirical formula is HO. But what if the material I'm dealing with is not HO, but H2O2? It might be important to know that at some points. So we need to have a way to figure this out. And we can do that. So we've only learned how to find empirical formulas, lowest whole number ratio of atoms in a molecule. We know that sometimes the formula of a molecule is a multiple of that, such as N2O4. So NO2 could also appear as N2O4. The same empirical formula, not the same molecular formula. In order to determine a molecular formula, we need to know the approximate molar mass of the compound in addition to finding the empirical formula. So I can find an empirical formula, and then if they give me a molar mass that's determined in some other experiment, then I can figure out what that molecular formula is. So 30.46% nitrogen, 69.54% oxygen. I can convert both of those to moles. So I get 2.174 moles of nitrogen, and I get 4.346 moles of oxygen. Setting up that ratio just the way we've done before, N to N sub 2174, O sub 4.346 reduces to NO2. But the molar mass of NO2 is 46.01 grams per mole. And it's not consistent with the information that they gave me, because they told me that the molar mass is between 90 and 95 grams per mole. So we have to figure this out. If I multiply the whole thing by 2 to get N2O4, the molar mass is 92.02, and therefore that is consistent. So N2O4 is the molecular mass that I'm looking at because it has a mass that matches with what I was told the molecular mass should be. Okay? So that's how we do that. Another example, molecular formula. Compound weight. Compound is 74.46 carbon, 4.43% hydrogen, and 20.10% oxygen. Molecular weight is 318.31 grams per mole. What is the molecular formula? So I know that my empirical formula is going to have C and H and O. How many moles of carbon is this? 75.46 divided by 12 is 6.289 moles of C. 4.43 grams of hydrogen divided by the 1.008 grams of hydrogen is 4.39 moles of hydrogen. And again, it's 3 sig figs because there were 3 given here. 4 sig figs because there were 4 given there. 20.10 grams of oxygen divided by 16 is 1.256 moles of oxygen. If we find the ratio, 1.256 moles divided by 1.256 equals 1 mole of oxygen. 6.289 moles of the carbon divided by the 1.256 equals 5.007 moles of carbon. 4.39 moles of hydrogen divided by 1.256 equals 3.50 moles of hydrogen. Well, that doesn't work, right? Because while these are both whole numbers, this one isn't. But if I multiply everything by 2, then this becomes 7, this becomes 10, and this becomes 2. So we have C10H7O2. And the molar mass of that particular thing is 159.06 grams per mole. We were told that the molar mass is 318.31. So that is not consistent again. If I divide the molecular weight by the empirical weight, so this number that they gave me in the beginning, divided by the empirical weight that we just calculated, then I see that that's 2.01. Okay, that means that I need to have 2 of those empirical formulas to make the molar mass. You must multiply the empirical formula by 2 to get the molecular formula. C20H14O24. What? Oh, that's a typo. It's supposed to be O4. I hate it when it does. There you go. That's better. Awesome. Questions, comments, problems about that? Chemical reactions and chemical equations. Oh my God, we're taking chemistry because we want to talk about chemical reactions and chemical equations. Where was I? Hit the wrong thing. Don't you love it when I do that? So we study chemistry because we want to learn how one atom or molecule is chemically changed into another substance. In order to be able to do that, we need to have a shorthand notation for what the process is, and we need to make sure that we have the same number of atoms of each type on the reactant side as on the product side. So mass can neither be created nor destroyed. So I have to have the same mass in the beginning as I do in the end, as long as it's in terms of moles. Okay, so H2 plus O2 goes to H2O. So hydrogen gas reacts with oxygen gas to make water. Okay, fine. But do we have the right number of things here? No, because I have H2 and H2. Awesome. O2 and O. That doesn't make sense because that implies that one of these oxygens just went away, didn't end up there. So we need to make sure that we balance this. And since this is O2 over here, we could multiply this by 2. That then gives me 4 hydrogens, which messes up this, and 2 oxygens. Since this is now 4 hydrogens, we need to multiply this by 2 as well. So 2H2O plus O2 goes to 2H2O. Okay? Now that we have 4 reactions, 4H on the reactant side and 4 on the product side, 2O on the reactant side, 2O on the product side. Yahoo! Now, I did some stuff there in the middle, right? To try and make it even. Yes, I did. So the reactants are the starting materials in a chemical reaction. Products are the substances formed as a result of the chemical reaction. So reactants go to products. Just to make sure that you understand that that's what we're talking about. We like to include the physical states of these things. We do this to make the calculations that come later this semester possible. So we like to know what physical states that we're talking about. This does become important when we talk about things like enthalpies and entropies and things like that. It's not important yet, but it will be. So we like to include those. It is important that you do so. All right. So 2CO gas plus O2 gas can make 2CO2. So 2 carbon monoxides plus oxygen gas goes to 2 carbon dioxide. When we include physical states, there are several we need designations for. G is gas, L is liquid, S is solid, and AQ means aqueous. For materials dissolved in water, it means aqueous. So NaCl is solid. You can have H2O added to it to make NaCl aqueous. While the water is explicitly shown here, it's not required, and often omitted by lazy chemists. So we just assume that since it says AQ, you know that means we put it in water, okay? So we don't explicitly state all of that, all right? Balancing chemical equations. Identify all reactants and products and write their correct formulas on the left side or right side of the arrow, respectively. So I need to know what substance I start with and what substance I finish with, and I need to make sure that those things are written correctly. I am not going to balance equations by messing with the subscripts within a compound. That's not how we do this. We cannot do that. So once this thing makes a compound, so if it's nitrogen dioxide, it can't become dinitrogen dioxide. Okay, we can't do it like that. We have to keep those things exactly as they appear, all right, and then use coefficients in front of them to do our balancing, okay? 2NO2 is 2 molecules of nitrogen dioxide. N2O4 is 1 molecule of dinitrogen tetroxide. They're completely different compounds, so we need to make sure that we've got what we need on each side. You want to balance anything that's not H or O first. Make sure that any element that appears only once on each side has the same coefficient on both sides. Then we want to balance anything that appears in 2 or more places. Dun, 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 dun. So we know that heating KClO3 will give us KCl and oxygen gas. By this process, KClO3 solid goes to KCl solid plus O2 gas. Chlorine. It said balance anything that's not HRO first. Make sure that any element that appears only once has the same coefficient on both sides. So there's 1 and 1. Woohoo! 1 potassium, 1 potassium. Potassium and chlorine are both awesome. But my oxygen is not. O is not balanced. 3 on the reactant side and 2 on the product side. So since oxygen usually has to appear somewhere as O2 on its own, then in other compounds you need an even number of O's. Okay, if it doesn't have an even number, we need to make it even. So the only way I can make this 3 into an even number is to multiply this whole thing by 2. So then I have 2 KClO3, but then I need 2 KCl's so that we still have the same number of K and the same number of Cl. And then since I have 2 times 3 oxygens, that's 6, then O2 needs to be multiplied by 3, and that gives me 6, okay? So like I said, multiply this by 2 with this, and that sorts out our oxygen. So now we have 6 oxygens here, 6 oxygens here. But now I have 2 Ks and 1 K. So 2 Ks. And then now I have 2 Cl and 2 Cl. Okay? So now we've got the same thing on both sides. So when I take care of one problem, chances are I've made another one. So that's something we have to keep track of. Now, how on earth am I going to do that? Well, I write a balance sheet. So typically when I do this, I will write down what I'm looking at. So my whole equation, and I typically will list each species as to how many are on the reactant side of the product side. This is the way we can do it as a different form of that table. So I can talk about carbon as a species. Sorry, not carbon, potassium. On the reactant side, I have 2. On the product side, I have 2. Chlorine. On the reactant side, I have 2. On the product side, I have 2. Reactant side for oxygen, I have 6. Product side for oxygen, I have 6. Now you can use fractions to balance equations, but since the math that follows the balancing is easier with whole numbers, balancing with whole numbers is preferred. Now, it's perfectly fine to do like 3 halves on something. You can absolutely do that. That's okay. But we typically don't work with them in that fashion. Now, if you do it and somebody says that it's wrong, let somebody know. So if Alex or D2L tells you that that is wrong, then let somebody know, because from a complete standpoint, that is correct. Okay? Questions, comments, problems on that? Now, let's talk about nuclear reactions, because we just talked about chemical ones. We talked about balancing those equations. Now we're going to talk about nuclear reactions. Now, all elements having an atomic number greater than 83 are radioactive. And this is from your textbook section 19.1. Somehow that got left off of the sections that you needed to study. So they emit particles or electromagnetic radiation spontaneously. It's called radioactive decay. Nuclear transmutations occur when nuclei are bombarded by neutrons, protons, or other nuclei. And so that causes that nucleus to change and become something else. So let's talk about the difference between chemical and nuclear reactions. Chemical reactions, atoms are rearranged by breaking and forming of chemical bonds. Nuclear reactions, elements or isotopes of the same element, are converted from one to another, from one element to a different one. In chemical reactions, only electrons in atomic or molecular orbitals are involved in the breaking and forming of bonds. Chemical reactions are accompanied by absorption or release of relatively small amounts of energy. And we'll talk about that later. And the rates of chemical reactions are influenced by temperature, pressure, concentration, and catalysts. And we'll talk about that later too. Nuclear reactions, on the other hand, we have protons, neutrons, electrons, and other elementary particles that may be involved in that. The reactions are accompanied by absorption or release of tremendous amounts of energy. And the rates of reaction normally are not affected by temperature, pressure, and catalysts. So only concentration of the things that we listed here. All right. Is it important that you remember all of that stuff? No, not really. But you do need to be able to look at a reaction and tell me if it's a chemical reaction or a nuclear reaction. So since I've shown you chemical reactions already, we know that's just rearranging of those atoms. Let's look at what a nuclear reaction would look like. In order to do that, we need to talk about the elementary particles and what they look like. Now, you will need to be able to write out the symbol given the name, or the name given the symbol, and you will need to be able to balance equations using these symbols. Sometimes that means predicting the missing particle, and sometimes it's translation of the words in the equation. Okay, this is an alpha particle, 4,2 or 4,2 alpha, 2 protons and 2 neutrons. This is a high energy helium nuclei consisting of 2 protons and 2 neutrons. Beta particle, 1 OE or 1 negative 1B, so a negative beta, is a high energy electron. Positron, 0 plus 1E or 0 plus 1 beta. This is a beta particle. We also call it a positron. You'll see both. Are particles of the same mass as an electron, but with 1 unit of positive charge. Protons, 11H or 11P. So it's just that positive nucleus. So it's the nucleus of hydrogen. It doesn't have the electron, it's just the nucleus. Neutron, 10N. This is its symbol. It's a particle with a mass approximately equal to that of a proton, but with no charge. And then we have gamma rays, which are symbolized by this gamma. Let me try and draw you a gamma. Looks something like that. It looks something like the fish, but not in the fish direction, if that makes any sense at all. All right. And that's a very high energy electromagnetic radiation. Okay, gamma. Think Hulk. That radiation turned him into Hulk. Okay. No, it doesn't actually do it, but just remember that. That's what we talked about. Now, remember that a nucleotide is an atom characterized by a certain atomic number, Z, and a certain mass number, A. We'll discuss that in more detail in chapter 19.1, A over Z time. So your mass number, atomic number, and the chemical symbol. Sorry, I copied it from somewhere else and didn't actually need that statement anymore because we're talking about 19.1 now. Woohoo! Balancing nuclear reactions. So balance the following. 25 over 12 Mg plus 42He goes to 11H plus AZX. Now, AZX is not something known. So we need to know what it is. That's what we need to identify is this particle that's right here. So the sum of the mass numbers on the reactant side has to equal the sum of the mass numbers on the product side. All right. So 25 plus 4 is 29. Since there's already a 1 here, we subtract that. And then we're going to get A equals 28. Okay. Some of the charges must balance also. So 12 plus 2 is 14. So number of protons has to be the same on this side and this side. That's why we're talking about those. 12 plus 2 is 14. Subtract 1 for the product that we already have, and the total is 13. So our AZX is then going to be 2813X, where X is going to be aluminum. Aluminum has 13 protons. So that's what we're talking about for that one. All right. And again, that's just based on what we found here. So 28 here, 13 here. If this is 13, then that has to be aluminum. Okay. Do it again. 21484 polonium plus 2 H2E, so 2 alpha particles, plus 2 electrons gives me 22286 Rn. All right. Now, is this balanced? 214 plus 2 times 4 equals 222. 84 plus 2 times 2 plus 2 times negative 1 equals 86. So 84 plus the 4 minus 2. Okay, it's 86. And that's how we get that. All right. Questions, comments, problems. Now, NASA uses the alpha decay of plutonium-238 as a heat source on the spacecraft. Write the balanced equation for this. Alpha decay plutonium-238. So an alpha particle is 42He. Plutonium-238 is 238 plutonium, which is 94. Plutonium is atomic 94, number 94. So 23894 plutonium goes to 42He plus some other particle. Okay, so 238 minus 4 is 234. 94 minus 2 is 92. Atomic number 92 is uranium, U. The heck? That's that. Yes, awesome. Copy and paste, make a mess. Yes, we did. Okay, fine. So now that we fixed that, so atomic number 92 is uranium, so 234.92 uranium. So 238.94 Pu goes to 42He plus 234.92U. Okay? Questions, comments, problems there? I hope not. Once we fix the problems, then we should the things that are there we should be fine. So let's practice balancing the nuclear equations. Beta decay in BK249, positron emissions in O15, and electron capture in I111. So 249 BK, so 249 on the top, BK is our symbol, 97 is the number for BK. And that's going to give off a beta, okay, which is this guy right here, 0, -1e. Remember, it's an electron. So that means that 249 goes to 249 because we have a 0 here, so it's 249 and 249. 97 has to go to 98 minus 1, so it has to be 98, and that's CF. We have positron emission in O15, so 15O, which is 8, gives me positron emission, which is 0 plus 1e. So my mass number is still 15, and my atomic number has to be 7. It has to go down 1 because of the positron emission, which gives me nitrogen. We have electron capture in I111. So 111, I, atomic number is 53. I'm going to capture an electron, which is an O -1e. That gives me 111 total on the top. 53 minus 1 is 52. This is telluride. Okay? Questions, comments, problems on that? Oh my lord, that takes us to the end of lecture 3. Now, what are things that you need to know from lecture 3? You need to know what the elementary particles are. You need to be able to balance an equation, and that means going from words to equation. You need to be able to do that. You need to be able to balance a chemical equation, and you'll need to do the same thing for chemical equations as well. You'll need to be able to translate the words into, use nitrogen dioxide to write NO2, iron 3 chloride to write FeCl3, that kind of thing. You'll need to be able to interpret that so that you can see what these things are. You want to make sure that 1, you can write the right species, and 2, that you can balance that equation. You need to be able to calculate from moles to grams, grams back to moles, moles to particles, particles back to moles. Okay? When in doubt, convert to moles. So those are the things that you should be able to do with that information. Okay? Now I hope that clarifies lecture 3. I'm going to go ahead and do lecture 4 soon so you can have that up and ready to look at. If you have any questions, comments, problems, anything at all, please, again, number of the lecture, approximate time code, and your question. And I will be happy to deal with that either in office hours or one of the other times you could talk to me or via email. Thanks. I appreciate it. Talk to you guys later.